Air, of course, is simply a mixture of gases. We live at the lower layer of the atmosphere. This not only makes it possible for us to breathe, but it is also the air that enables us to fly. All we really need to know about air right now is that it has substance, that it is denser near the Earth and gets thinner at higher altitudes. Thus, it exerts force when it moves. And as far as air being invisible, the aerodynamicists have come up with a way for us to see it in a smoke tunnel. It's done by drawing streams of smoke into the air. If we can see the air, then perhaps it will help us answer our beginning question: how do airplanes fly? We'll start with a double-winged model in the airflow. The action of the air between the wings will demonstrate a basic principle of aerodynamics. Now, by animation, let's study the airflow in greater detail. First, note that its pattern suggests it is passing through a tube-shaped device. Next, notice that the entrance and exit of the device are the same size. We can measure the openings and find that the ends are each 10 square inches. The middle part is squeezed, creating a throat of 5 square inches. Now, if we direct smoke lines through the device, its pattern will show that something happens to the air where it goes through the narrowed part. What we find is that when the airspeed is 100 miles an hour at the entrance of the device, it is also 100 miles an hour at the exit. Yet at the same time, the speed at the narrow part is considerably higher. It can easily be understood, therefore, that the air increases in speed as it passes through the smaller opening. But the interesting thing is that in order for the air to go at the faster speed through the narrow part, something has to balance this change in velocity, this speed difference. What changes is the air pressure in the narrow part. This pressure is significantly lower than the pressure at either end. But what does this have to do with flying? If we cut the model in half, we would have a profile similar to an aircraft wing section, called an airfoil. You can see how helpful it would be to lower the pressure over a wing. Why? So that the comparatively higher pressure under the wing would push or lift it into the area of lower pressure above the wing. That's part of how an airplane flies. Some of today's wings have what is called a symmetrical airfoil, with the same curvature on both sides. In level flight, this design will tend to equalize the pressure on the top and bottom of the airfoil. But watch what happens to the airflow when we incline the airfoil a few degrees. We have caused a low pressure on top of the wing. This creates a pressure difference between the top and bottom, giving us lift. The airflow striking the fixed wing airfoil of an aircraft, or the aircraft itself, is called the relative wind. The direction of the relative wind is always opposite to and parallel with the flight path of the airplane. In level flight, therefore, the relative wind and the flight path are horizontal and parallel. The center line, or chord line of the airfoil, however, even in level flight, forms a small angle with the flight path. We call this angle the angle of attack. We have given it the symbol alpha. What happens when we increase the angle of attack? When we increase alpha, we increase the pressure difference. This creates more lift. But there's a limit on the lift. See what happens to our smooth flow when we increase the angle of attack further. This is where the stall begins. If the alpha angle is increased even more, lift will decrease rapidly until there is total stall, with a great loss of lift, and turbulence so great it may buffet the airfoil. As a pilot, you'll need a healthy respect for stall. The three aerodynamic principles we've just seen, lift, angle of attack, and stall, are so important we ought to put tags on them. This symbol might serve to remind us of the principle of lift. Lift is the flying principle that, as air is accelerated over an airfoil, it reduces pressure and thus overcomes weight. Let's tag angle of attack with an angle and the Greek letter alpha. As you recall, alpha is simply the angle formed between the relative wind and the chord line of the airfoil. But its importance is in the fact that even small variations affect the amount of lift. Stall might be represented this way, with emphasis on the fact that the air flowing over the top of the airfoil ceases to follow the upper curved surface and breaks away in eddies of air. Stall, of course, is the result of an alpha so great that the air can no longer flow smoothly over the curved top surface of the wing. Stall for many airfoils begins at about 15 degrees. Why all this talk about airfoils? Well, as we've said, wings are airfoils. But note the other airfoil shapes: the vertical tail, the horizontal tail, even the propeller, and in a sense the fuselage itself. All are aerodynamic shapes. The design of an aircraft is determined by a careful consideration of many aerodynamic shapes and how they totally respond to the principles of lift, angle of attack, and stall. And because these airfoils are so important aerodynamically, let's get to know their language. To begin with, they have a rounded leading edge and a pointed trailing edge. The center line from the center of the leading edge to the point of the trailing edge is called the chord line. We also speak of camber of an airfoil. Camber refers to curvature. We've spoken of the forces of lift, angle of attack, and stall that work on an airfoil. But there are two others. First, we need a force to make the plane go forward and create the relative wind. This is called thrust. Since thrust is another of the major aerodynamic forces, we'll tag it with a symbol representing a propeller and an arrow. Thrust is generated by an engine which exerts the force to move the aircraft forward. Aerodynamically, the airfoils of the propeller blades form lift or low pressure in front of the blades, pulling the propeller forward. But what about thrust in the case of jets? The exhaust gases and air are pushed out of the exhaust with such tremendous action that the balancing reaction thrusts the aircraft forward. But when the airfoil, or any object for that matter, is thrust through the air, there is a retarding force of air resistance and inertia. We call this drag. Let's represent drag as a backward arrow and a parachute. Drag, too, is one of our major aerodynamic forces. Now we've come to the point of examining all the forces acting on an airfoil in flight. Lift, we know, is what holds up the airplane. Putting it another way, it overcomes the weight of the airplane. Thrust is what moves the airfoil ahead and overcomes drag. When an airplane is flying straight and level and is not accelerating, these forces are in balance. Thrust equaling drag and lift equaling weight. But we don't just fly straight and level. We have to get up there and back down, and we want to move around. Suppose we increase power. We increase thrust, and while it is out of balance with drag, speed will increase. But drag will also increase with speed until these forces are in balance. By increasing the speed, we also increase the lift capability of the aircraft, because more air is flowing over the airfoil. The lift is maintained equal to weight by changing the angle of attack with speed. In steady level flight, all forces are in balance. Thrust equals drag, and lift equals weight. And this forces in balance relationship is so important a principle of aerodynamics that it too should have one of our tags. Let's make it with 4 equal arrows for lift, drag, thrust, and weight. But let's not leave our discussion of these forces without noting that they may be acted on or influenced by outside factors.